Hi folks, Mr. S here again. This lesson is on gases. In this lesson, we will discuss kinetic molecular theory, real gases versus ideal gases, gas variables, unit conversions, gas laws, gas stoichiometry, and then we will discuss a lab which involves finding the molar mass of a gas. When we take a look at kinetic molecular theory of gases, which is essentially particle theory that you learned in grade 9, it states that gas particles are tiny and spread apart. Gas particles are in constant random motion. Gas particles have no volume. Gas particles have no intermolecular forces. And collisions between gas particles are elastic, meaning when gas particles collide, they don't lose any energy. This brings us to the idea of real gas versus ideal gas. Ideal gases follow the kinetic molecular theory to the T. Particles have no volume, collisions are elastic, there are no interactions or intermolecular forces between particles, and these gases obey gas laws at all temperatures and pressures. When we take a look at a real gas, particles do have volume, energy is lost during collisions, intermolecular forces do exist. However, these gases tend to behave more like ideal gases and obey kinetic molecular theory at higher temperatures and at lower pressures. Why? At higher temperatures, particles have high kinetic energy and they are farther apart. And at low pressures, they are also farther apart and as such behave more like ideal gases. Typically, when we study gases, we study the four following variables. We study the moles of gas. We study the volume of gas, which is measured in decimeters cubed or in liters. We study the pressure of gas, which is how often gas particles hit the sides or the walls of a container. And then lastly, we study the temperature, which is measured in kelvins. You will notice that our gas laws that we will study will be comparing or studying the relationships between two or three of these variables. The diagram below here shows three scales of temperature. We are going to be focusing on Celsius and Kelvin, specifically Kelvin when it comes to gases. Points to note here are 0 degrees Celsius is equal to 273 Kelvin. 0 Kelvin is equal to negative 273 degrees Celsius, which is known as absolute zero. It's a hypothetical temperature at which all molecular motion stops. Typically, when you're doing gas law problems, you'll be asked to convert Celsius to Kelvin. To do that, you simply add 273. If you are asked to convert Kelvin to degrees Celsius, you simply take away 273. Pressure is how often gas particles hit the walls of a container. I can increase the pressure inside this container by either reducing the volume or by adding more gas particles. The common units for gas are Pascal, kilopascal, atmospheres, and millimeters of mercury. You should know how to convert between these units. Here's the relationship. 1 atmosphere equals 100 kilopascals, which equals 100,000 pascals, which equals 760 millimeters of mercury. You might also be asked to convert to another unit called torr, which stands for torricelli, and we can add that to this list as well. If you were asked to convert between these, let's just do a quick sample question here. If I had 2 atmospheres and I wanted to convert that into millimeters of mercury, so this is 2 atmospheres being converted to millimeters of mercury. I will take the 2 atmospheres and I would multiply it by the ratio between millimeters of mercury and atmosphere. I know that 760 millimeters of mercury equal 1 atmosphere. Notice how I wrote this known ratio. I put 760 millimeters of mercury on top and I put the atmospheres at the bottom. Keep in mind that when you are solving, when you are converting between units, the unit that you want to convert to should always be in the numerator. And the unit that is in the question should always be in the denominator. You will cancel the atmospheres and then you will just multiply that by 2. A couple of temperatures and pressures that you should be familiar with is STP, which stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius or 273 Kelvin. Standard pressure is 100 kilopascals. Standard ambient temperature and pressure is 25 degrees Celsius, which is room temperature, or 298 kelvins. And standard pressure is, once again, 100 kilopascals. It doesn't hurt to memorize these. Next, we will talk about gas laws. Gas laws study the relationships between the gas variables. You will recall the gas variables that we typically study are moles, volume, temperature, and pressure. Boyle was the first person to study the relationship between volume and pressure. Here's the formula for Boyle's law. It states that at constant temperature and constant number of moles as well, as the pressure increases, the volume decreases. Keep in mind that if I want to study the relationship between any two variables, I must keep the other two variables constant. If I'm studying the relationship between volume and pressure, moles and temperature must remain constant. This states that pressure and volume are inversely related. What that means is that as the pressure goes up, the volume goes down. Charles studied volume and temperature relationships. At constant pressure, and as well, once again, if I'm studying the relationship between volume and temperature, moles and pressure remains constant. So at constant pressure, in all of these cases, moles is also remaining constant. As the volume increases, temperature increases. This is what we call a direct relationship. Volume is directly proportional to temperature. It's important for you to know this because when we have a proportionality sign, that means that if I were to double my temperature, my volume will also double. Gay-Lussac's law, or Gay-Lussac, studied pressure and temperature relationship. Again, here, volume and number of moles remain constant. As the pressure increases, the temperature increases. The pressure is also directly proportional to temperature, meaning that if the pressure goes up, so does the temperature. Vice versa, as the temperature goes up, so does the pressure. Combined gas law can be determined by combining these laws. Combined gas law allows you to study impact of changing two variables on one additional variable. And then lastly, the ideal gas law. This is the gas law that we will be studying in more detail coming up. Avogadro's law states that moles and volume are proportional. In other words, as you increase the number of moles, the volume of that container will increase. Here's the formula for Avogadro's law. And here is the graph of Avogadro's law, which essentially states that as the number of moles increases, so does the volume. You should also be familiar with graphs associated with Boyle's law, Charles' law, and Gay-Lussac's law. Boyle's law was the one where pressure and volume were inversely related with each other. This tells you that as the volume increases, your pressure decreases. This is volume and temperature. We know volume and temperature are directly proportional to each other, which means that as the temperature increases, so does the volume. And then lastly, pressure and temperature are also directly proportional to each other. Tips for solving gas law problems. If you're looking at Boyle's law problem, and in fact, anytime you're looking at inverse relationships, in this case, we're looking at pressure and volume, when the pressure is doubled, volume is halved, and vice versa. When the pressure is tripled, the volume goes down to 1/3. I am getting this from this. So if pressure is proportional to 1 over V, which means they're inversely proportional. If I were to double the pressure, that means that this becomes 1 over 2. If I were to triple the pressure, that means that this part of this equation here becomes 1 over 3, which means my volume goes down to 1/3. When I'm looking at Charles' law, or when I'm looking at Gay-Lussac's or Avogadro's law, here, since we have direct proportionality, if I were to double the temperature, again, this temperature is Kelvin temperature. You have to be mindful of that. If I double the Kelvin temperature, my volume gets doubled. If I triple the temperature, then my volume also gets tripled. At times, you will hear the question say absolute temperature. So if you hear the word absolute temperature, they are talking about the Kelvin scale. Molar volume is another concept that you should be familiar with. It states that 1 mole of any gas at standard temperature and pressure, STP, you will recall STP is 0 degrees Celsius or 273 kelvins and 100 kPa. 1 mole of any gas at STP occupies a volume of 22.7 decimeters cubed. This is any gas. It could be hydrogen gas, carbon dioxide, it could be oxygen gas. You take your pick. The formula for molar volume is Vm equals volume divided by the number of moles. This is very handy when we start to do some gas stoichiometry questions. The ideal gas law. The ideal gas law can be easily derived by looking at Boyle's law, Charles' law, and Avogadro's law. The ideal gas law is PV equals nRT, where P is pressure, and this is in kilopascals, V is your volume in decimeters cubed. N is the number of moles. T is our temperature in kelvins. And then R is known as the universal gas constant. And this has different values. In our case, in IB, we are going to be using this volume, 8.314. Types of ideal gas law questions that you will typically get. If I'm looking at this equation here, you can get a question where you're given three of the unknown variables and you're asked to find the fourth one. So, for example, I can give you the pressure, I can give you the volume, I can give you the temperature, and I can ask you to find number of moles. R is a constant, so it doesn't hurt to memorize that number. You could also be asked to, given pressure, volume, and temperature, find the mass of a sample. If you were asked to do this, notice that there is no mass in this question. You are going to have to find mole first. You're going to have to find the mole first, and then you're going to have to convert the mole to mass. You could also be asked to convert, this should be 3 and this should be 4. You can also be asked to calculate the density of a gas. Now, density of a gas is mass over volume. If I have the volume of the gas, I can easily find the moles using the ideal gas law and convert it to mass and divide the mass by volume. It depends on if the question is asking you to find the density in grams per liter or grams per milliliter. If it's in milliliters, the volume must be converted to milliliters. And lastly, you would be asked to use the ideal gas law in a stoichiometry question. Let's take a look at a stoichiometry question that involves gases. In this case, the question says, find the volume of hydrogen gas produced at STP when 32.69 grams of zinc, which has a molar mass of 65.38 grams per mole, reacts with excess hydrochloric acid. This is zinc, that's hydrochloric acid, which produces zinc chloride and hydrogen gas. This is what I'm interested in. So we have 32.69 grams of zinc. We have an excess amount of this. And I am asking you to tell me what volume of hydrogen gas is produced at STP. This is your typical stoichiometry problem. However, here we are now involving a gas. HCl is in excess, which means we don't have to worry about it. To solve this question, I need to be mindful of the mole ratio between zinc and hydrogen gas, which is 1:1. What I'm going to do is I'm going to convert this to mole. And then we're going to use the mole to determine the mole of hydrogen, which is going to be the same because the mole ratio is the same. And then afterwards, I'm going to use the mole to determine the volume of the hydrogen gas. Now, I know you folks know how to do this. You simply divide by the molar mass of zinc. We also know how to do this. In this case, the mole ratio is 1:1, so I don't really have to do anything. But here, you'd be using the mole ratio from the balanced equation. I want to focus on this step 3. So if I call this step 1, and if I label this as step 2 and label this as step 3, I want to focus on step 3. How do we find the volume of hydrogen gas? So to find the volume of hydrogen gas, you can actually use two methods. I can either use the ideal gas law, which is PV equals nRT, or I can use molar volume. I can use molar volume because the question said at STP. We know that at STP, 1 mole of any gas has a volume of 22.7 decimeters cubed. If I am using the ideal gas law, I have STP, which means I have my pressure, I have my temperature, and I have the number of moles because I found the number of moles here. I can plug that number of moles here. I also have the value of R. I can rearrange this for volume, which turns out to be nRT over P. Making sure that my units are all correct, I can plug all the numbers in here and I can go ahead and find the volume. If I wanted to use the molar volume, if we go back for a second and take a look at the formula for molar volume is volume divided by number of moles. So, molar volume equals volume divided by number of moles. In this case, I am looking for my volume. Therefore, volume is equal to molar volume times the number of moles. And again, I can just simply plug the numbers in here. My molar volume is 22.7 decimeters cubed, and my moles is whatever moles I found in this question here. I plug those numbers in, and I am able to find the volume. Lastly, we will take a look at a gas stoichiometry problem which involves gases, and there is not much information given. Let's take a look at an example like this. Let's say we are doing combustion of methane, and all my reactants and products are in the gaseous form. If you were asked that you have 5 liters of methane with excess of oxygen, can you tell me how many liters or what volume of water you would form? So, how many decimeters of water will you form? We first have to make sure that the equation is balanced, and by putting a 2 there and a 2 there, the equation is now balanced. Notice in this question, I'm not giving any temperature, any pressure. I cannot use the ideal gas law here. Here is where I'm going to use the second part of Avogadro's law, which states that equal volumes of all gases at the same temperature and pressure contain the same number of particles or same number of moles. If you take a look at hydrogen gas, nitrogen gas, and helium gas, these gases are all at the same temperature and pressure, and if you actually count the dots, they all have the same number of moles. What does this mean? To simplify this for you, that essentially means that this mole ratio is actually equivalent to volume ratio. If I translate this in terms of moles, it says 1 mole of methane reacts with 2 moles of oxygen gas to produce 1 mole of carbon dioxide plus 2 moles of water. I can now also explain this in terms of volume, according to Avogadro's law. 1 decimeters cubed of methane reacts with 2 decimeters cubed or 2 liters of oxygen to produce 1 liter or 1 decimeter cube of carbon dioxide and 2 decimeters cubed of water vapor. This essentially means that the mole coefficients that I have in the balanced equation can also now be used as volume ratios. Now this is very simple. If I know that 1 liter or 1 decimeters cube of methane produces 2 decimeters cubes of water vapor, 5 would produce 10. We can easily set up a ratio and figure that out. Lastly, we will take a look at a lab which involves finding the molar mass of a gas. And in this case, this is a lab that we did in class. This is a lab that you could do as an IA if you wanted in the future. Essentially, what we will do is we'll take a lighter. That lighter there contains a compound called butane, and we light the butane under a graduated cylinder. We watch the video on this, and you can easily find other videos on YouTube on this. We light the lighter underneath, and what happens is the gas that's coming out of here goes in there and it displaces the water that is in your graduated cylinder. By the way, the graduated cylinder was filled with water and it was inserted upside down into this container of water. And then what happened was, as the gas was released, the gas pushes the water down. This is known as collecting gas by downward displacement of water. So the way we do this lab is we find the mass of the lighter before and after. So in this case, we will wet the lighter, we will find its mass, and then we will carry out the experiment, and then we would find the volume. We can actually measure the volume of the gas by, it's called downward displacement of water, because water is being displaced downwards. We measure the volume of the gas. From this step here, we can find the mass of this butane that is being used. We can use the volume from here. And then it says to use the ideal gas law to calculate the moles of gas. How do we do that? Well, we know ideal gas law is equal to PV equals nRT. I will have the pressure, I will have the temperature, because this experiment will typically be done at room temperature. And at room temperature, your temperature is 25 degrees Celsius, which is 298 kelvins. Your pressure is atmospheric pressure, which would be 100 kilopascals. And your volume, we would be getting from this experiment, and then we can figure out the number of moles by just rearranging this equation. Once I have the moles and the mass, I can find the molar mass. How? If you recall, moles is mass divided by molar mass. Well, molar mass is mass divided by number of moles. This mass here is what we determined in step 1. Moles is what we determined in step 3. Once you do that, you have now found the molar mass of your gas. Thank you.